Hello, my name is Indara Garcia, and this project will aim to find the best material for an artificial blood vessel. The purpose of this project was to find the best material for an artificial blood vessel, and the study will be focused on the carotid artery, which measures 5.11 millimeters in diameter and 0.47 millimeters in thickness. Some of the other specifications are the flow rate of a healthy adult male, which is found to be 0.01 kilograms per second. This flow rate will be increased by 5 times the normal flow rate in order to simulate extreme conditions that the human body may undergo. The normal blood pressure of an adult male is 120 over 80 millimeters mercury, and for this project the blood pressure will be 120 millimeters mercury, because that's the pressure inside an artery when there's blood pumping through it. Also, the body temperature of an adult male is around 310.15 Kelvin. The primary specifications that the material must be able to meet in order to be considered a good candidate are biocompatibility, so that it will ensure that the material does not harm the surrounding body or the blood. The pressure that is exerted through the material must be close to that is present in the human body, and the material must have a low strain to prevent problems such as low blood pressure. This material must also be economical in order to increase the profit that it will bring to the company. So the three materials that are being considered are thermoplastic polyurethane, polytetrafluoroethylene, and polyvinyl alcohol. TPU is biocompatible and biodegradable, which will allow it to mend the damaged artery and be disposed of in the body. It also has a high tensile strength of 58 megapascals, which will allow it to be made way thinner, which can be ideal for smaller blood vessels such as veins. PTFE is biocompatible and also has a high tensile strength. It has a tensile strength of around 7.58 megapascals, as well as a high axial tear strength, so the material will not tear easily. This is perfect for an artery because it will have higher pressure since it's coming directly from the heart to the rest of the body. PVA is also biocompatible and non-hemolytic, which will ensure that it will not harm the surrounding blood cells. Additionally, it has a high tensile strength of 4 megapascals. So 3 separate designs were made for each of the materials, and all of these designs have the same diameter and thickness, which were specified above, and their lengths were different. Their lengths are 1 millimeter, 10 millimeters, and 100 millimeters. So this will bring us to a total of 9 different models. 2 separate flow simulations were designed for the 9 different models. The first simulation had a normal inlet flow rate of 0.01 kilograms per second, and the outlet conditions were set to the environmental pressure that was defined earlier, the 120 millimeters mercury. The second simulation had an elevated flow rate of 0.05 kilograms per second, which is 5 times as large as the original. The outlet conditions were once again set to environmental pressure. For these simulations, the maximum pressure and the maximum shear stress were recorded. So each of the 9 models had 2 different maximum pressures because they had 2 different flow rates, and each of those pressures were used in a static simulation in which the ends of the blood vessel were fixed to simulate an attachment to the rest of the artery. The pressures gathered from the previous flow rates were used on the inside of the blood vessel, and the maximum strain was recorded. So this table shows the results from the normal flow rate for each of the materials at each of the lengths. The maximum pressure changed as the lengths increased, but it remained the same for each of the materials at each length. So you can see that as the length increases, so did the pressure, and the maximum strengths change for each of the materials at each of the lengths. Furthermore, this table shows the results for elevated flow rates. So the pressure and strain changes followed the same pattern as for the normal flow rate, And in this one, the difference will be that most of the values in this table are larger than those in the normal flow rate, except for the values of TPU, which seem to, the strain values seem to be lower than the ones before. So the graphs that you see here show a graphical representation of the strain for each of the material at the different lengths. The graph on the left represents the normal flow rate, while the graph on the right represents the elevated flow rate. PTFE had the largest strain, and TPU had a consistent low strain. The strain for P-val was inconsistent for the two different flow rates. However, the strain seemed to remain between TPU and TPFE and PTFE. So this table shows the cost of the material. It's going to be the cost per gram, and TPU has a cost of 11 cents per gram, while P-val has a cost of 9 cents per gram, and PTFE has 4 cents per gram. So the material chosen for the artificial artery is going to be P-val. P-val demonstrated an overall small strain and a low cost. This material has a high tensile strength, so it can be made thin as needed, and it won't harm the body because it is also biocompatible. P-val also has a high axial tear strength, which will provide tear resistance for stresses or loads that are provided in the axial direction. So this is particularly important because arteries contain more pressure than regular blood vessels, so a high axial tear strength will be very beneficial for arteries. So yes, thank you so much for your time.